A final example, once again, is 0, 0 over 0 indeterminate form. And once again, we will approach this with polar coordinates. If you remember, this is actually an example we did with the two-path approach, and we saw that this limit does not exist. Let's see what that looks like when we use polar coordinates, if we want to use the polar coordinate technique. We're going to switch to polar coordinates, so we'll have a limit as r approaches 0. X is r cosine theta, so we have x squared, r cosine squared theta in the numerator, r squared cosine squared theta plus r squared sine squared theta in the denominator, replacing x and y with their polar coordinates. That's the limit as r goes to 0 of r squared cosine squared theta over r squared. I can factor the r squared out of those two terms, and I'm left with a cosine squared theta plus sine squared theta. Now that cosine squared theta plus sine squared theta is a very well-known trig identity. That quantity is equal to 1. And so we have the limit as r goes to 0 of r squared cosine squared theta over r squared. The r squareds cancel. And the limit as r goes to 0 of cosine squared theta, well, there's no r's in cosine squared theta, so that's just cosine squared theta. Now, what does that mean? That means the limit we get depends on our angle of approach. It depends on what theta is. And so we can say that the limit does not exist, which is consistent with what we found from the two-path test earlier.